Now let's see how related rates can help us solve this problem right here on our computer screen. So let's look at the wording of the problem. At noon, ship A is 20 nautical miles due west of ship B. Ship A is sailing west at 25 knots, and ship B is sailing north at 23 knots. How fast in knots is the distance between the ships changing at 4 p.m. Okay, and so there's a little note here to explain what a knot is. So 1 knot is a speed of 1 nautical mile per hour. But so I also need to further clarify that. So a nautical mile is a term that the sailors are using. So when we are traveling by car on land, then everybody know how long 1 mile is. So on the ocean, then the sailors are using 1 nautical mile, but truthfully it equals to approximately about a 1.5 mile. Okay, but this is really just for you to know, extra information. May be beneficial for you, but I don't see how it's directly applied. I don't see how it can be much useful in our problem, because everything is in terms of nautical miles anyway. We are completely on the ocean, on the sea right here, so nothing related with land. So here, just for your extra information. All right, so now let's look back and dive into the wording of the problem line by line right here to extract our information. So at noon, so I'm only seeing noon here as a time point. Noon is only a time point. So ship A is 20 nautical miles due west of ship B. So we basically having 2 ships. So our 2 ships on the ocean. So, and let me draw a picture like this. Think about the compass right here. Then that's way up on my board is north. And so if that is north, then heading this way is west. And heading this way over here to the right on my hand right here is east. And so south is down here. So that means I'm going to use my 2 little dots right here, 2 little points on my board to represent. So this is where ship B is at, because the description said at noon, at that instant, then ship A is 20 nautical miles due west, and due west means ship A is on the west side of B, and about 20 nautical miles away. So that's where I call that. So I call that ship A right here, and this distance has already been right at that instant, right at that time point at noon. Then we knew that these 2 ships are 20 nautical miles, and still allow me to just use miles. Of course, we're on the ocean, we're on the sea, so it's nautical miles by default. So that's the first information we knew. And let's get back to the board here. The wording on the computer screen, and find out and extract out further information. And the idea now is that right at that instance that we are seeing the 2 ships, then they're both moving. It's just right at that instant. Then this ship A is already 20 nautical miles to the west of ship B. That's and the formal term due west of ship B right there. But aside from that, they're both moving. They were already moving. And so ship A at that instant is sailing west at 25 knots. Okay, and this is where and this clarification is now making it clear about it's a speed. So knot is the units for speed. So 1 knot is 1 nautical mile per hour. So ship A is sailing west at 25 knots, and ship B is sailing north. Okay, so sailing west, A is sailing west, and B, okay, is sailing north. So on my picture, let me describe the situation like this. So from that instance, and continuing from what was currently going on, then ship B is heading this way. It's sailing north, and ship A is sailing west. That means ship A continue to travel further into the west and getting further away from B, and B is heading up that way. Okay, heading north. And my arrows are a little misleading, but ship A is actually sailing a little faster than ship B, because ship A is sailing at the constant speed being 25 knots. So the reason I draw the two the two rays pointing out right here is because think about that. Time just goes on, time goes on, and as these two ships are moving at the same time, at the same every instance that both of these ships are moving away from each other, then think about some t time later after the noon time point, then let's say in an hour later, then this ship B makes that much distance, and that ship A makes that much distance, depending on how fast they go. And the good thing is they are going on with constant speed. Okay, and so in the end, think about if you take a photo shot at any time instance after that noon point right there, then it's gonna form into a triangular setup right here. So ship A will make some further x distance. And actually, you know what? Why don't I use a name that's, consistent with the name of the boat itself? So my variable, how about some a distance? So ship A is at this point right at noon, at that time instance, and ship B is right here. But think about some time instant at time t later. Okay, at some time t later, then ship A makes some additional lowercase a distance, and the same would be right here. So ship B at the same instant t hours, t minutes later, after noon point, then ship B is gonna make some b distance. But any of these distance, I use the lowercase letter. So lowercase a for how much distance the ship capital A made in t minutes, in t hours, and this is for B. The lowercase b is for ship B. Okay, so in the end, it does actually form into a triangular setup. And so at any point of time, at any instant of time, in the end, the two ships make some distance with each other. And so right at noon, and they are being that much apart, and then as time goes on, then they are so think about these 2 points right here. We'll keep getting further out and further out, because as they are moving away from each other, okay, then as they keep sailing in their own direction, in each of their own directions, then that distance, and let's name that distance x. And really, when it comes to these kind of problems, you have your own choice completely to name these variables right there. I just want to point out that how these variables are related. Okay, but in the end, we just form, and it's a good thing, it's a good understanding about these compass setting right here, because they're all always meant to be perpendicular right here. Okay, and so now here's how I see it. What we have now is at any time, okay, at any time t, okay, it could be t hours, t minutes, or whatever, but we will have a triangular setup right here. And my picture I'm drawing here is meant to be the distance, okay? The distance, how much distance they have made, at some t time. And so at any t time right here, then this is what I see right here. This length of my triangle setup right here is going to be not simply just a, but it's actually a plus 20. That's the longer leg of my right triangle. And then the other edge right here at any time t, then ship B will produce the distance that being part of this triangle, distance B. But now in this triangle setup, then the distance between the two ships in the end in this triangle setting is acting as the hypotenuse of our right triangle. And so now Pythagorean theorem famously guarantee for us that a plus 20, that longer leg, plus the shorter leg, the square of the two, the sum of the two squares equals the sum of the two squares of the legs right here equals to the square of the hypotenuse. Okay, so it equals x squared. So a plus 20 all square is this longer side of our right triangle, and this b right here is our shorter side of the triangle. But a plus 20 all square plus b square must equal x square. And what we have found here is the relationship relating our three variables, our three distance variable. Okay, and so once we found this, it's sort of like half of the problem is done already. Okay, so now ready for the next thing. So let's get back to our wording of the problem, and here's what I'm seeing. So the question is asking how fast is the distance between the ships changing at 4, but how fast is the distance between the ships changing? So that means, as the goal of the problem, we need to find, because this x right here is the distance between the two ships. So what we're looking for, and how fast, it's a rate of change. And in this problem, it's a motion problem, and things are moving, so it's a speed, right? So we're looking for dx dt. Okay? How fast that x distance is changing. I'm not necessarily increasing, it could be decreasing, right? But how fast is it changing over time? Okay, and so we want to find dx dt. And so now once we have identified our goal, and now we know that we need to find the rates in terms of t right here, and that's kind of like, there will always be different clue here and there for us to identify what kind of variable that we need to differentiate in terms of. And so let me once again bring you back on the computer screen, and there are other information that in pieces of information that we can find right here. See, ship B is sailing north at 23 knots, and knots is 1 nautical mile per hour. So this is once again the kind of speed we're looking at, the kind of rate of change we're looking at is in respect to time right here, per hour. That's how I can recognize that any of our rates is a rate in respect to time. Okay, and so now after all of that clarification, then I am going to go ahead and get straight into, I'm not too worried about hunting for the other given information in our problem yet. We will come back to that. But my point is, I really want anyone studying with me to really apply immediately your skill in finding related rates right at that instance where you have successfully identified your equation that relating the variables. Okay, then just immediately apply your skill. And then once you've had that, and on top of our goal, we have already identified here that we need to find our dx dt, then we're going to hunt for the information we need in order to fulfill what we need. Okay, and so right from here, I am going to move to my other board. So a plus 20 all square plus b square is to equal x square. I am going to get straight into differentiating my left hand side and my right hand side in terms of t, because I have already identified that all of our rates in this problem are in terms of t, as I have argued earlier. And so now the process that we've learned back from the general lecture regarding related rates is here. So now I'm gonna need to differentiate in terms of t this first term, a plus 20 all square. Okay, and I need to also differentiate the b square term, and I also need to differentiate the x square term, and so far I already wrote that notation. But now keep in mind, t is nowhere, our variable that we're differentiating in terms of is nowhere found among the equations. So that means any of our current variables is a function of t. Okay, so any of these a, b, and x, they're all functions of t. And so, in other words, they're all implicit functions of t. And so now this first term gives me, according to the chain rule, there's an outside and the inside is right here. There's my inside, and the outside is a square. So now, and you have seen that hopefully fluent enough throughout my general lecture on related rates. So here allowed me to do that in a faster pace compared to how I was doing that through the steps in the lecture, but here I'm looking at 2 times a plus 20, and I need to multiply with the derivative of the inside. But taking the derivative of the inside, that term simply gives me a 0 because it's a constant. And this term right here is the implicit function a of t. And that means taking that derivative together, it gives me just simply a dA dt. Okay. And now I'm done for the first term. Now let's differentiate this b squared term in terms of t right here. So doing that, just like how I've done that back in the lecture, that term here gives me b squared times dB dt. Okay. So that term gives me 2b times dB dt. Okay, and all the explanation can be very similar, can be made very similar to how I deliver this back in the general lecture about finding how to derive your related rates equation. And so the same thing here on the right hand side of the equations. Now x is a function of t, so outside is a square, inside is the unknown, the implicit function of t, x of t. And so now taking the derivative in terms of t, I'm looking at 2x times dx dt. Okay, and so of course we can only carry on with the application problem here after you, hopefully my viewers are fluent with how to take implicit differentiation here. Okay, and so now we have an equation that relates 3 rates together in this equation. And of course, earlier on the other board, I was pointing out that our goal is to find out the value of dx dt, how fast our distance here, the distance between the 2 ships, are increasing. Okay, or I shouldn't even say increasing, maybe it's a little too soon to say increasing, but basically that distance is changing. So if at the end, after the calculation is done, and if we came to a positive value, a positive rate, and that means this distance would be increasing. But if that distance here shrinks, then it's going to be, a decreasing. I mean, if that dx dt turns out to be a negative, then that distance would be decreasing. Okay, so I just want you to get into the habit of let the calculation result speaks. Oh, okay. So now, we know that we need to solve for this value right here, and it could be positive or it could be negative. But then solving for that value depends on a lot of other factors. We need to find out what our x variable must be at that instant, and as well as the dB dt value, or the value for b, and the value for dA dt, and the value for a right there. So there are still quite a few information to find out. And so now I'm going to get back on my other board and let's nail down some further information. I have to erase this beginning writing of mine, and I'm going to leave the picture here for a reason. Okay, and now let's look on the computer screen here. So ship A is sailing west at 25 knots. So now we actually know the dA dt. That highlighted information right there is now valuable for us, that we know dA dt. Okay, lowercase a, that's what I meant. So dA dt is actually 25 knots. Okay, and further, let's look for other information. So ship B is sailing north at 23 knots. Okay, so another piece of information we have now identified. So dB dt is also given at 23 knots. So these are constant speed. That's a good thing, constant speed. Okay, and now further, the question was asking, how fast is the distance between the ships changing at 4 p.m.? This information, at first, it seems a little irrelevant at 4 p.m. But now think a little further. The problem right in the beginning started out introducing us, or the problem began with at noon. And so from at noon, if we're treating noon as a time point, then from noon to 4 o'clock, how much time do you think that has gone by? 4 hours. So we can take that information there and think about it this way. Okay, so from noon, okay, and to 4 p.m., really we're looking at t. That's the same as saying t equals 4 hours apart. Because if noon is the starting point, right, then the point when we first notice the two ships, then 4 hours later, that when it hits 4 p.m., okay, then 4 hours later, and the problem is I'm a little rushing actually. It's actually, yes, it's 4 hours, but we need to put this into our time. I just now noticed. And so it's 4 hours because our speeds were indicating that it's, in 25 knots per hour, 23 knots per hour. Okay, and so now think of it this way. Good thing is that our ships are all traveling in constant speed. So think about in 4 hours, then see, in 4 hours, then the distance for ship A, the distance ship A makes is 4 times 25. It's the way how we find distance once we know a constant speed and time. And so that's 100. But 100 is only that distance here. We already had that constant 120 there. Okay? But so A is 100 knots, nautical miles. And in 4 hours, ship B will make, okay, 4 hours times 23 right here. And that gives us 92 right there. Okay. And so now, all that information now is ready for us. And actually, we also need to find, our x distance right here. So, but now once we have laid down A and B, then things are quite, simple for us. Because our equation earlier was saying that, I recall, A plus 20 all squared plus B squared to equals x squared. If we recall from that equation, then here's how we solve the problem. I need to again erase my little space here, some of my space, to make further work. But now I'm looking at A being 100 plus 20, because that the initial distance between the two ships are here. So that square gives me 120 square plus 92 all square. That will equal x squared. And so now we're on our way solving for x right here. And so x here is just simply taking the square root, a complete square root of 120 square plus 92 square. That's how we can find our values for x. Okay, and so now I can keep erasing more stuff further out. Okay, so my calculation here, right, so calculation of mine shows x to equal 151.21 nautical miles. And for short, I'll just use miles. But of course, we're on the sea, so it's nautical miles. Okay, so now we have all the pieces we need. So I have to recall again. A equals 100. It's that instance right at 4 p.m. Okay, 4 hours later. And then B is 92. Okay, so now I take all of these information, including dA dt and dB dt and all of these information right here, ready for substituting it into our other equation on the other board here. And so now, and we also can simplify that 2 away. that common factor 2 from both sides of the equation, making things a little less complicated for us. Okay. And so now A equals 100. So now I'm looking at 100 plus 20. I'm looking at 120. Okay, times, and the ADT is 25. So I'm substituting 25 into my dAdt, and plus my B value was in 4 hours at 4 p.m. And that instance gives me the B value being 92. And then at that instance, the ship B was traveling at 23 miles per hour. 23 knots per hour. And then at that instance, then ship A, the distance between the two ships is 151.21. Okay, now that's multiplied with dx dt, and that's what we need to solve for. Okay, so have a good clear look at our overall equation. All right, and so I am going to do a little bit of calculation and ready for moving on to the next step right there. All right, so on my first board, now I must erase all of this information here. All right, so picking up from the previous step, right from here, then we can find our final dx dt can be found by simply the sum on the left-hand side of our previous equation there is going to give me 5,116, and dividing that by 151.21. Okay, so where did I get that 5116 from? That was from all of that sum here on my left-hand side of the previous step. And then I was dividing that sum being 5116 by 151.21 there. And so my final dx dt was calculated to be 33.83. Okay, and this is in appropriate units, in its appropriate units, knots. Okay, 33.83 knots. All right, and that's how we were doing. We applied related rates in solving this motion problems, and it's two ships, right, and creating two variables, and including that variables being the distance between the two ships. There are three variables being involved.